while we were recording so everyone get a chance. What I'm talking about, the question came up, do you need to show work on test? Now, this class hasn't had a test yet, but hopefully we'll get one fairly soon. The answer is I can give more partial credit if I can see your work. So it's up to you whether you do that for me or not, but if you do, I can give more partial credit. So that sort of indicates I'd like to see your work, but that's completely up to you. If you're so confident in your answer and you just want to give me the answer, if it's right, that'll be fine. But I'd rather see your work. Okay. Any other questions, concerns, issues? All right. Now, I don't think this is a slide. Oh, maybe it is a slide we start. Yes, it is. So this is a slide we start from. So let's get this up here. There we go. Can everybody see the slide? It says we are. Anyone who cannot? Okay. Now I'm going to, you can't see this, but I have a toolbar that is smack in my way. I have to move that down out of my way. Okay. And this toolbar, well, I think that'll be okay. All right. If there are no more questions, we were on in Chapter 5, Integration, Section 5.5, Integration by Substitution. And we're doing Example 7. If you've got this text, it's on page 337. I'm sorry. Other classes tell me when I turn my head, I fade out, so I'll try to talk into the microphone. Okay, we talked about the general rule, power rule for integration, but I see no special reason to do that. Just use your substitution and it works. Okay, so here's an example. Okay, here's the problem we're looking at. The integral, forget this over here. Okay, here's the problem we're looking at. The integral of 3 times 3x minus 1 raised to the 4th power times dx. Okay, now in any other circumstances, I would be tempted to take this 3 and put it outside the integral. And actually, that's not a bad idea here either, but don't do it yet because we're going to see what's going to happen. Another option for working this problem, if anyone wanted to take it, is multiply 3x minus 1 times 3x minus 1 times 3x minus 1 times 3x minus 1. That's 3x minus 1 to the 4th power, and you'll have a big, long 4th degree polynomial. Okay, if anyone wanted to take the time to do that, you're a harder worker than I am. I prefer the easier way, and the easier way is the U substitution. Now, what do we look for in U substitution? The simplest part of the innermost part of the most complicated part of the problem. Well, obviously, the most complicated part of this problem is raising it to the 4th power, which I just told you could do it one way, and that's a long, tedious way to do it. So here's the innermost part of that power, 3x minus 1. Let that be your u, okay? Now, they didn't show that here, but that's what they implied. If 3x minus 1 is your u, your du is just 3 dx. Well, here's your 3, there's your dx, and that's why they grouped those together and made it your du, and made this u raised to the 4th power. Okay? Now, why in the world wouldn't they have taken the time to say, let u equal this? They basically did it here, but just not telling you that's what u was equal to. Well, then how do you integrate u to the 4th du? Whoops, hold on. iPhone's trying to get in, okay? Let me see if I can remember who iPhone is in this class. I have them in a couple classes. Is that James?
Yes, sir.
James, is that you?
Yes, sir.
James Mullins? Okay.
Yes, sir.
All right. Got you here. All right. Let me just check and see how many we're up to. We're up to 14 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, because Amina and Laron are on together. Okay. So, we're on page, James, Chapter 5, Integration, 5.5, Integration by Substitution. If you got the text on page 337, example 7, just about the middle of the page, the A part. And what we just said, if you start with the innermost part of the most complicated part of the problem, most complicated part here is raising something to the fourth power. Innermost part of what you're raising to the fourth power is 3x minus 1. So let that be your u. Du then would be simply 3dx. And that's why they separate and make the 3dx du over here, and then they say u is equal to, u is raised to the fourth power, which all you had to say was let u equal this, du is equal to that, and you have this line right here. Well, then if you're integrating u to the fourth du, that's the power rule. That's why they say the general power rule. It's u to the fifth over 5. That is the antiderivative of it. And then you put what u is, 3x minus 1, raise it to the fifth power, divide it by 5, and add your constant of integration c. Are there any questions about that? I don't particularly like the way they did it, but it was perfectly correct. And if you like to skip steps and, play this kind of game, seems like to me it's so easy to do it the way we do all of them. Let u equal this, du's equal that, plug those in, do that, then plug back in what du is. If there's no questions, we'll move to the next one. Any questions? All right. Well, I forget. I have to click on the screen before it will advance. There we go. All right. So here's another part. E to the x plus 1 times e to the x plus x dx, the integral of that. Now this one actually would just about be as easy if you did just multiply this. Just use the FOIL method, multiply. This would be e to the 2x plus x e to the x plus e to the x plus x, okay? That wouldn't be too bad to do except for that term that's x e to the x. That would be something we haven't done. We haven't done yet. Wait a minute, somebody's trying to come in. I can't see their name. Can you see who this is? I'm going to admit them, but I can't see who it is. Is it Cal? I believe that was Cal. See, at this point, when someone's trying to come in, Zoom blocks out their name. And I don't know why, okay? But Cal, was that you coming in?
Yes, sir.
Okay, good deal. That's who I thought it was, so I put you down. Okay, good deal. We're on... There goes my pen again. All right. We're on Chapter 5 integration, 5.5 integration by substitution, page 337 if you got the text, example 7, and we're on the B part. Okay, we said one way you could do the problem. I don't think anyone else is coming in. So, okay. Is multiplied through, except that you have an x e to the x term that we don't know how to do yet. So that's not a great idea in this problem. So a better idea, what's the more complicated looking part of this problem? Is it this part or the second part? Well, to me, the second part's a little more complicated because it's got an x. This one just has a 1. So let u be e to the x plus x. Okay? What's du then? Well, d of e to the x is simply e to the x, and d of x is 1 dx. Well, here's your e to the x plus 1 dx. There's your du, and then your u to the first power is e to the x plus x. So why put a plus 1, a 1 there? That's just u. And then you're integrating u du, and that would be u squared over 2 plus c. And what's u? E to the x plus x. Okay? Just like they show here. So let's see how they proceed. I can't proceed until I click on the slide again. This is such an aggravating thing of Zoom. Okay, so it's u to the 2 du, u squared du. Integral of u du is u squared over 2. I'm sorry, I said du. U squared over 2. U was e to the x plus 1. And that's what you got here, e to the x plus 1 squared divided by 2 plus c. There's your answer. Now, again, I see no reason to not say let u equal this and du's equal to that. That's what they're doing in effect, but they're doing it as if you don't have to write it down, which you don't. But if you see this better, by all means do it. Any questions on the B part? Okay, let's go to the C part. Okay, now this block is in the way, but I don't think it's blocking anything now. Here we have the integral of 3x squared times the square root of x cubed minus 2, then times the dx. Well, what do you think the most complicated part of that problem is? The part I never like to have in there, it's the radical, okay? That's the most complicated part of the problem. What's the innermost part of the radical? X cubed minus 2. Let u equal x cubed minus 2, and that's exactly what they do here without saying it. Then du would be what? If u is equal to x cubed minus 2, du would be 3x squared dx. And that's what makes their du. 3x squared dx. They just moved it over here with that. That's your du. So what do we have here? I don't like the radical, so I write it as u to the 1/2 power times du, the integral of u to the 1/2 du. Well, we know what that is. Raise this by 1. That's 2 halves. 2 halves plus 1/2 is 3 halves. That'd be u to the 3 halves. But remember, we have to divide by the 3 halves, which is the same as multiplying 2/3. So it's 2/3, if I could get my cursor back, 2/3 u to the 3 halves power times, yeah, that's it, 2/3 u to the 3 halves power. What is u? X cubed minus 2. So you plug that in. So here's how they get their answer. Here's your u to the 2/3 power, 3 halves power, I said 2/3, 3 halves power divided by 3 halves. Once that window gets out of the way, that stinking rectangle, it's all Kyle's fault. When he came up, it went up there to block him. It didn't want us to see him. There it is. Okay. Here's your u to the 3 halves power. U is x cubed minus 2 to the 3 halves power divided by 3 halves plus c, which then you can take divided by 3 halves and make it 2/3. So let's see if they'll do that. Yes, there it is. If that box will get out of the way. Because isn't that blocking your view, folks? This rectangle here, isn't it blocking some of this wording down here?
Yes, and then it fades out.
Okay, but here it's fading out. So here's your answer. 2/3, which is the inverse of 3 halves, times x cubed minus 2, that was your u, raised to the 3 halves power plus c. Don't go back and put it in radical form. I see no reason for that. Leave it in exponential form. So much easier to write, and you don't have the confusion, well, what do you cube here? It really doesn't matter, but you don't have that to worry with. All right, any questions on the C part? Anybody? Okay, let's move on to D. So here we have the integral of minus 4x divided by 1 minus 2x squared dx. So 1 minus 2x squared in parentheses squared dx. And what's the most complicated part of this? Obviously, it's the thing in the denominator that's squared. So what's the innermost part of that thing that's complicated? 1 minus 2x squared. Now, someone else might say, well, it would be the 2x squared. That's the inner part of that, isn't it? Or just x squared. No, keep it together. Otherwise, you have so many u's and v's and w's there, you'll get confused. Keep it the innermost part of the more complicated part. 1 minus, so let u equal 1 minus 2x squared. What's your du then? Derivative of 1 is 0. Derivative of minus 2x squared would be minus 4x. Look at that, dx. Well, there's your minus 4x dx. There's your du. And what is your u part? u to the minus 2. Again, I don't like radicals. I don't like variables in the denominator, so I always write them in exponential notation rather than denominators or radicals. So this becomes your u to the minus 2, which they write up here as if it's a secret up there, and this is your du, what you got from taking the derivative of this. Well, what's the antiderivative of u to the minus 2? Someone help me out on that one. Antiderivative of u to the minus 2. What's the rule? Add 1 to your exponent. Negative 2 plus 1 is merely a minus 1. So it's u to the minus 1 over a minus 1. Okay? Because your new exponent now becomes your denominator. So that will be just minus u to the minus 2. Okay? And when you do that, this is your u. So it's a minus to the minus 1. Minus 1 over 1 minus 2x squared. Now, whether they leave it in radical notation or, not radical, rational notation or power notation, I don't know, exponential notation. So this is how they wrote it. Whoops, whoops, here comes somewhere else. Jose, he was here, and I think he just came back. So I've already marked him here once, so that's all he gets. But let me admit him, I'm talking about him, but I forgot to put him back in. So he must have got booted out. Okay? So once you do that and you find the integral of antiderivative of u to the minus 2 is minus u to the minus 1, which is effectively what this is, then you plug in what u is, and u was 1 minus 2x squared. Okay? So let's see if they'll finally write it that way. They, for some reason, it won't advance until I click on it. Okay? There it goes. Minus 1 over 1 minus 2x squared plus c. This is that thing to the minus 1 power. Put it in the denominator to the first power. It's just that. So there's the answer. Any question on that one? Does it make sense? Okay, let's see if we can get e to come up. There it is. All right. Now, the antiderivative, or the integral of cosine squared x sine x dx. What's the most complicated part of that problem? Well, sines and cosines are about equivalent, but this one's squared, that one's not. So I would say the most complicated part would be the cosine squared. Well, what's the innermost part of that? Well, the innermost part of cosine squared would just be cosine. So let u equal cosine x. That's effectively what they're doing here, except they're skipping the step of saying that. So let u equal cosine x. What's your du then? Derivative of cosine is minus sine x dx. We only have a sine x, so we have to, depends on which way you do it, multiply by minus 1 to have a minus 1 in front of the sine x, because minus and minus is plus. So put a minus on the outside, or here's the way I like to do it. Du is equal, u is equal cosine x. Du is equal to minus sine x dx. We only have a sine x dx, so divide by minus 1, or multiply by minus 1, and make minus du equal sine x dx. So that's your du then, but you bring that minus that was interjected there out front, okay? And then you have the integral of u, because remember, let u equal cosine x, so this would be u squared, and here's your minus sine x dx. See, that minus and this minus makes it a plus. That's what you started with, a plus. So that's why you have to have them both. This is your du, and so u squared du, you know what that integral is, u cubed over 3. And what's your u? Cosine x, so it's minus cosine cubed x divided by 3, or 1/3, minus 1/3 cosine cubed x plus c. If I could get, let's see if the Oh, there it is down there. Minus cosine x cubed. Now that, I don't know why they did this. I guess because they did it here. You can put it in parentheses and cube it, like they put this in parentheses and squared it. I didn't notice that. Or you could have written this minus, don't put a parentheses, cosine cubed x over 3 plus c. That's how I would have written it. They changed it back. But since the original problem was like this, I see no reason to change it back here. Let's see if they do change it again. No, they don't. All right. So that's example 7. Any questions on example 7? They did all the work, okay, but hopefully you followed all the steps. Were there any questions on why any of those steps were there? Okay. If not, what we go to next is change of variables for definite integrals. Okay. So far we've done, I think, all indefinite integrals. Okay. But if you have to do a definite integral, there's a couple ways you could do it. You could do everything like we just did with indefinite integrals, go to the u's, and then at the end of the problem, plug in what u was, and then plug in what your definite integral was. That's a couple of extra steps. This is the lazy man's way of doing it, which I think makes a lot more sense. So we've always got to change variables because you've got to have the u in there. So we're going to show you a couple ways to do that. When using the u substitution with a definite integral, it is often convenient to determine the limits of integration for the variable u rather than convert the antiderivative back to the variable x again and then evaluate the original limits. Now, I have a block of your pictures or names or whatever over here that's blocking some of that writing. Is that blocking any of the writing for you? Like this "the" here? Do you see the whole "the"? THE? Yes or no?
Yes.
You do? Okay. So therefore, I'm not going to move that. It blocks mine, but if it's not blocking yours, I'm fine. Okay. This change of variables is stated explicitly in this.
You can drag it to the bottom.
Well, yeah, I've already got the other one to the bottom. I could drag it to the top, but then I can't read the top. It's going to be in my way somewhere. So if it's not in your way, I'm happy with it here. Okay, but thanks, yeah. Appreciate that. Okay, so here's theorem 5.15. The change of variable for definite integrals, and this block's going to fade out, and I'll try to get it said before it comes back. No, it's not blocking anything. Okay, if the function u is equal to g of x has a continuous derivative on the closed interval a to b. Okay, if u equal gx, that's going to be your substitution one, by the way. If that has a continuous interval on that closed interval a to b, and remember a is the lower limit of your integration and b is the upper limit. So if that g, that interior part there, innermost part, the most complicated part of the problem, if that g is continuous on that interval, and if f is continuous, okay, f is the thing you're taking of g, your composite function, is continuous on the range of g. In other words, when g takes on the a value, you find a value for g. G takes on the b value, you get another value for g. And if f is continuous between those two, f of a and f of b, g of a and g of b, then this is how it works. Now, let me tell you, this is way more complicated looking than what it really is. Okay? So, here's your outermost function. Your most complicated part is your f of g of x. What's the innermost part of that complicated part? G of x. So basically we're going to let u equal g of x, then g prime of x is going to be, g prime of x dx is going to be your u prime, du basically, okay? So then you'd have a f of u du. But you see, you change your variable from going from a to b of x, that's your x values, to when you evaluate g at a, that gives you g of a at the bottom value, because remember, u is equal to g of x. So put in the a for the x, and you get g of a, that's some number, that's your bottom down here. put in the b for the g because that's what u was. U was g. So g of b is the top. And then that gives you, if you can do this integral over that range, you got it knocked. And again, this with letters, I think is more complicated seeming than it is when you actually put numbers in. But hopefully this makes sense for you. Okay, so let's do one. All right. Going to evaluate the integral from 0 to 1 of x times x squared plus 1 cubed dx. Now, do you want to see me do this on the whiteboard first, or do you want me to just talk through it as they show the steps? You tell me. Whiteboard or PowerPoint?
Can we see it on the whiteboard?
Okay. I'm perfectly happy to. I prefer it that way. If I had the old system, I could write on this very screen, but I don't have it, so this means I have to go to the whiteboard. Sorry about that. If we'll go to the whiteboard, there it is. Okay. Now you see I have another taskbar up here that now I have to move. It's not, you can't see it, but I can. So I got 3 taskbars I'm having to shift around so you can see. And the other thing I'm going to do is shift the whiteboard this way as much as I can. Okay, I think I've got it as far as I can. Okay. So now you have to put up with my writing. What we have now is the integral from 0 to 1. You asked for it, you got it. Of x times x squared plus 1 I keep getting a box down there, and I don't know. Oh, I guess it's just coming in and fading out, so it's not mattering any. X squared plus 1, and that's cubed if I can read my book correctly. That's raised to the 3rd power, and then you have a dx. This is always fun. Okay. Now, again, no reason to do anything differently from what we did before. Does anyone want to hazard a guess of how I'm going to approach this? I'll look for the innermost part of the most complicated part of the problem. Most complicated part is raising it to the 3rd power. That's your f, okay, if you're thinking in those terms, okay? The innermost part of that f is this part, what's in the parentheses. So that's going to be my u. Let my writing stinks here. Let u equal, that's written too close, let u equals x squared plus 1. This is what we were doing before on their screen. Okay? And your next statement is then, always this, let u equals this, then what in the world is, I can't get my e to work, there it goes. Then, that's a pretty ugly e, that's a pretty ugly then. Then du, yuck, is equal to, and you take the derivative of x squared plus 1, what do you get? Anybody?
2x.
dx, don't forget the dx. 2x dx. Okay, very good. Now, here's a problem, folks. You have an x dx up here. You don't have a 2x dx. So I want to divide away to 2 because I don't like 2. No, that's not it. Divide both sides by 2. Okay? Now, that wipes them out over here, but it introduces a 1/2 when we rewrite this. So this integral is going to become, now I'm not through with this, but I'm going to get as far as we did last time. This integral becomes, I'm leaving off the limits now. Don't worry about those yet. Okay? Your x dx, that's this times this, is 1/2 of du. So I'm going to put the 1/2 on the outside because that's just a number. It doesn't have to go inside. 1/2 the integral of, and then this is, here's your u cubed, and then this part was dx. So that's what we had, similar to what we were doing before, u cubed du. That's an ugly d. Okay, u cubed du. The du over 2 was x dx. There's the x dx. There's the over 2 part. There's the du part. And then this part was u cubed du. Now, before we evaluate the integral, which is the easy part, we have to fiddle with the limits. Okay? Now, right here we saw that x is going from, because see, this dx indicates what this represents. This is x equals 0 to x equal 1. Well, when x is equal to 0, what in the world is u? Right here. When x is 0, what is u? 0 squared plus 1, right? What's that?
1.
1. Perfect. And when x is 1, what is u? X is 1. This would be 1 squared plus 1. Didn't know you'd be doing such high-level math this early in the morning. Oh, well, midday now. 1 plus 1 is 2. Okay. So it's going from 1 to 2. U's going from 1 to 2 when x went from 0 to 1. You just plug them in here. Here's what u is, or u are, or whatever. Plug in the x values here to get your u values here. Does that make sense? Now let's evaluate our antiderivative. What is the antiderivative of u cubed du? And again, increase the exponent by 1. 3 plus 1 is 4. And then divide by that new exponent, divided by 4. But this one, evaluated at u, you plug in the values of u. Oh, well, I'm sorry. I forgot my 1/2 out front. That 1/2 there, okay. 1/2 times this. So let me put this in a bracket here. But over here I don't write a bracket. I put a vertical line and go from 1 to 2. Okay. So this will be, and by the way, you can go on and pull this 4 out with the 2 and make that 1/8. To me, that's easier than dragging around that fraction that's not going to change any. So just make that 1/8. 1/2 of 1/4 is 1/8. And then plug this in. Does anyone know what 2 to the 4th power is? Anyone? You're plugging this 2 in for that u. 2 to the 4th is
8.
16. And I think I can do the next one. Minus 1 to the 4th power is, let's see, let me scratch my head. Where's my calculator? Oh, it's 1. Okay, so this becomes simply 15/8. Okay, that's an ugly 8, but let's see if it works. Oh my goodness, I think they got the right answer too. Good for them. All right. Now, you saw me do it. Let's step through and see how. Any questions before I erase this? Or go back to my other screen? Any questions? Okay. Let me... (5,5) is where we were. Okay. And I found out if I go back to current slide, it takes me back there. Yeah. Now this is this rectangle blocking out evaluate the integral? Anybody?
We can see it.
You can see it, okay. Sometimes it blocks it, sometimes it doesn't, so that's good. Okay, so how you evaluate this? Just like we did before. Here's the most complicated part, the cubing part. What's the innermost part of that? X squared plus 1. Let that be u. Let's see if that's what they do it. Yes, to evaluate the integral, let u equal that innermost part, x squared plus 1. Then what's your next step? Once you have a let u be this, then du is equal to 2x dx. Then du is equal to 2x dx. Why they don't write it under here, I don't know, but it's fine, anywhere they want to write it. But up here you have an x dx, you don't have a 2x dx. So to divide out the 2 down here and put it with the du, that'll be 1/2 du is equal to x dx. And we have the x dx up here, and then this would be u cubed, and that would be times 1/2 du. But before substituting, determine, I like to go in and substitute first, but they like to do it before that. That's fine. Determine the new upper and lower limits of integration, and you do it from this line right here. This indicates when x is going from 0 to 1, so what you want to get is u going from what to what. When x is 0, u is 1, because this would become 0 plus 1, so that would be 1. And the upper limit would be x equal 1. You plug x equal 1 here, you get 1 squared, which is 1 plus 1 is 2. So that's your new limits, 1 to 2, rather than 0 to 1. Now, they aren't always going to be just move them up a number. You have to actually evaluate them every time. So let's see what they got. When x equals 0, u is equal to 1. When x equals 1, u is equal to 2. So yeah, that's what we got for our new limits for u. We're getting away from the x and just going to deal with the u's. You can still see this square, this inside the rectangle. So now your integral from 0 to 1 of x, blah, 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 is 1/2, that's dividing by 2, remember, 1/2 the integral from, why in the world, okay. They threw in this extra step. They kept the limits the same, even though they already calculated. Kept this the same, only moved this as being your u cubed times 2x dx, that's your du, but they put the 1/2 out here, so this 1/2 cancels that one, though you don't want it to, and that gives you back what you started with. So look, make up your mind. Which way you're going to do it, go for it. What they're doing is right. It just seems like that was an unnecessary step. So what this becomes then, this 1/2 pulls down as 1/2. That integral that was for x's now is going to be for u's, so that's going from 1 to 2. And then this was your u cubed, and that was your du. Okay? And we can do that integration. That's 1/2 of u fourth over 4, evaluated from 1 to 2. And that would be, again, they did it the hard way, but it's perfectly fine. 1/2 of 4 minus 1/4, that's what you get when you plug in 16/4 is 4 minus 1/4 is 1/4. So this will be 3 3/4, which happens to be 15/4 times 1/2 would be 15/8. They got it their way. I found it easier. Pull out the 1/4 with this and make it 1/8, and then you just add 16 minus 1 is 15. However you want to do it, as long as you get the right answer. That is 15/8. And see, that's why I like to see your work. If you've done it a correct way, even though it's not the way that the test bank has it or anything else, I don't care. I want to see how you did it, what your thinking was, and that's why I say, if you show me your work, I can give you more partial credit. Now, if you chose a way that didn't work, and that's where you made your mistake, then that gives me something to talk about and remind you of, and hopefully teach you through that, well, here's why this one won't work here. this way. Well, here's what you didn't do. You forgot to change your limits. Whatever it is, that enables me to see where you went wrong. Just seeing a completely wrong answer and not knowing any way how you got there. You could have just been guessing. You could have been playing darts and had numbers on the dartboard, and whatever number you put. Don't do that. Never mind. I didn't say that, did I? Okay. So that's example 8. Any questions? Okay. Let's see what else they do here. Notice that you obtain the same result when you rewrite the antiderivative. Remember when you had it down to this thing, 1/2 of u4 over 4 in terms of the variable x. Well, what was your variable x? It was, I've forgotten now, x squared plus 1. Raised to the 4th power, and put that in there, but not change your limits to u's, but leave them for the limits for x. And if you did this, then this would be 1/2, that's still there. And you plug the 1 in here, be 1 squared is 1 plus 1 is 2. 2 times 2 raised to the 4th power is 16 fourths. That would be your 4. Minus, and you put a 0 in for x, this 0 in for x, you get 1/4. So there you got the same thing. 16 fourths minus 1/4 is 15 fourths times 1/2 is, there it is, the way they did it. 1/2 of 4 minus 1/4 is 15/8. To me, that's the longer way to get around your elbow to get to your ear than going straight to your ear. Okay. Any questions on that? They showed you 2 ways you can do it. I find it easier to change the limits, but if you like to keep the x's and go back to x, that'll be fine too. Any questions? All right. Last sort of topic we're going to hit here is how we, again, be lazy, okay? What if you have a perfectly even function or a perfectly odd function? Now, I don't know if you remember back in your long days ago when you did pre-calculus, whenever that was, high school, college, whenever, when you did pre-calculus, and they talked about even and odd functions. They almost talked about it's one or the other. Guess what? The biggest class of functions is neither, neither even nor odd. In fact, several of those we've just been doing were neither even nor odd functions. But if you happen to have a function that's either even or odd, you can make life a lot easier. And again, this is a lazy man's approach here. Even with a change of variable, integration can be difficult. Boy, what an understatement. Occasionally, you can simplify the evaluation of a definite integral over an interval that is symmetric about either the y-axis or about the origin by recognizing, oh goodness, why did that happen? Why did that happen again? There we go. Sorry. Okay. By recognizing the integrand as either an even or an odd function. Here is an example of an even function. Okay. Now what do you notice about this? If you're going from minus a to plus a, if those are your limits of integration for this even function, guess what? This area under here is precisely the area under here. So why don't you just double the value from 0 to a? Hey, guess what? I can usually plug in a 0 and get the right answer. Okay, that's a pretty easy thing to do. Negative a, if I'm squaring, cubing, doing whatever I'm doing to that function, I might do it and then forget to do the minus for the integral. If it's a 0 there, it's a 0. So basically the easier thing here to do, if this is an even function and it's going across a symmetric range or domain, you might say here, about the y-axis, you just take the integral from here, 0 to a, double it, and you get the total area under that curve between minus a and a. However, if you had an odd function like this one, this is minus x. That's all that is, minus x. And you're going from minus a to a. Well, the area up here happens to be a positive area of that triangle. but down here is the negative area of that same triangle. Guess what that area is going to add to? 0, because you're adding a positive area to a negative area, and they're exactly the same size, so that adds a 0. Whereas an even function, you integrate that, you double from 0 to a. Okay. So here's the theorem that tells you what to do. If f is an integral function on some closed interval minus a to a, notice that's a symmetric interval about the origin. If f is an even function, and you're evaluating from minus a to a, and the integral of that is f of x dx, integrating that even function over a symmetric interval, you just double the interval of the, I'll get it right in a minute, double the integral of the interval from 0 to a. Oops, here's somebody coming back in. I can't see the name. Oops, can someone tell me who that was? It blinked out before I could tell. Who just came in? Was it a new person or someone that had been here?
Oh, it's on this one. My laptop died.
Okay, yeah. Who was that? Jesus? You went out and came back in?
Onesimus.
Okay. Oh, Onesimus. Okay, great. I couldn't see this. Zoom blocks out the name, so I can't read it. That's very helpful for the host to not know who's there. Okay. So that's saying if it's an even function, you just double the integral on the interval from a to b. 0 to a, sorry. But if f is an odd function, and you're integrating that from 0 to a, that's always going to come out 0, because on one side it's doing one thing, on the opposite side it's doing the opposite thing. When you add those together, you get 0. Nothing. Even function does the same thing on both sides, so just take half of it and double it. Easy way to go, because this integral going from 0 to a is usually easier to evaluate than going minus a to a. This one is just 0, so that's pretty easy. So let's see if they have that last example. For some reason, I have to click on the slide to get it to advance, and yeah, they do. So here's what they've got. Oh my goodness, evaluate this definite integral. And boy, could they pick something that was weirder for their example. Okay? It's the integral from minus pi halves to pi halves. Sure enough, we have symmetric interval across the y-axis. Okay? Here you have sine cubed x cosine x plus sine x cosine x dx. Okay? Now, I don't know where to begin to try to break this down for you. I'll do it here if you can tolerate this. Sine is an odd function. Okay? I hope you remember that. It starts negative, goes through 0, and becomes positive. That's on either side of the x-axis, from minus pi halves to pi halves. It's exactly what it does. Starts at minus 1, goes through 0, and goes up to plus 1. Half of a sine curve each way. So that's an odd function. Okay? It's raised to an odd power, so you would think it would stay odd. Multiplied by an even function, but it's sort of like pluses and minuses. If you have a minus sign and you multiply it by a plus, it's still going to be minus. So this part is going to be odd. This part is an odd times an even. That's going to be odd. So this is an odd function. Can anyone tell me the answer then? Anybody? The integral of a symmetric, across a symmetric interval of an odd function.
0.
0, you got it. Okay? That was real fast. He did a lot of that in his head, didn't he? Now, let's see how they do it. Okay? All right, I was afraid they were going to do that. Okay? What is the most complicated part of this part of the function here? The cubing part. What's the innermost part of that cubing part? Sine x. Let u equal sine x. Okay? Well, if u is equal to sine x, well, no, they're not doing it that way. You could. I'm sorry. I didn't read enough of what they were doing. Here's what they're doing. They're testing even and oddness. If you remember this from pre-calculus algebra, this is one way to do. Plug in a minus x for the x and see what happens. Okay? If you plug in a minus x here for x, a minus x here for x, a minus x here for x, and a minus x here for x. Well, sine of minus x is going to be minus sine x. Cube of minus sine x, and you get minus sine x cubed. So it's negated. This, plug that into an even function, and it's the same as cosine of x. So this will be negative, this one will be positive. This one will be negative because sine of negative x is going to be opposite of what sine of x is. It's the odd function. And cosine of negative x is going to be the same as cosine x. So that's going to be an even function. It is an even function. So that's going to be the negative of that. So this f is an odd function. It's minus sine cubed x cosine x minus sine x cosine x, which is exactly the opposite of what your f of x is. F of minus x is exactly the opposite of f of x. That makes it an odd function. Okay? If it was exactly the same, that would make it an even function. If it's neither exactly the same nor exactly opposite, guess what? It's a neither function. And most functions, not the one they're giving you here, most functions are neithers. Okay? So that's going to be minus f of x. That makes it an odd function. Because it's symmetric about the origin from over the interval from negative pi to negative pi halves to pi halves, you can apply the theorem and see that's going to be 0 without having to do a single substitution or anything else, just testing for even and oddness, which is a pretty easy test most of the time. Sometimes they can get really hairy if you have radicals in there and things. You have to visualize what the graph looks like and stuff, and then it'll be maybe a little harder to see. But this one, not too bad. So from the figure here, you can see that the two regions, and now I can almost hear you say, doesn't that look like a lot like a sine curve? It kind of looks like a sine curve, though it's not. It's only going, sine curves would go from negative pi to positive pi. That would be your range of period of 2 pi, from negative pi to pi. So this isn't the same. This is from negative pi halves to pi halves, but where this on this side is going up, on this side is going exactly the opposite, even to here and there. So those are exactly opposite functions. Sorry. I'll need losing my voice. Hold on just a minute. Sorry about that. Don't know if that's going to help, but it feels like it should. Okay. So because of that, it is an odd function. This area is exactly equal to that area. Okay? Now, and because I delayed too long there, I'll wait till the little rectangle. Now, this one is blocking it, right? This rectangle. The big rectangle doesn't seem to block, but this little rectangle does. But it fades out because f is an odd function, and this is an symmetric about on the y-axis, on the x-axis. That integral is 0. Without having to graph, without having to substitute anything else. If you did your substitution, did everything you're supposed to do, you see it equals 0. You go to all that work to get nothing. Okay, this is a little easier. However, because one lies below the x-axis, the other above it, the integration produces a cancellation effect, giving you 0. Even though these two areas are the same, this is a negative area, that's a positive area. One's above the x-axis, one's below. When you add them together, you get nothing. Okay, not the total area, the sum of the two areas. And that's the end of section 5.5. Any questions on 5.5? Okay. Homework exercises here would be either 5 or 7. They're both at Calc Chat. 5's at Calc View. So, folks, if you don't have this book and you're using another book, work those problems. That'll be fine. But if you want to see these problems, you can go to calcchat.com. You don't need this book. You don't need a code from this book. You don't need anything from this book. All you have to do is go to that website, calcchat.com. If you want to see a fuller explanation of it for that one problem, number 5, you can go to calcview.com, calcview.com. Now you have to find the book. You'll have to navigate the site because he uses those two sites for all his text. So you'll see how to do that. I've never done it, but I think I have confidence you can manage that. Okay. Then the next group, any of the odds from 9 to 27. They're all at Calc Chat. The odds are 15's at Calc View. Do either 29 or 31. They're both at Calc Chat. 29's at Calc View. Do 33, I'm sorry. Yeah. It's also at Calc Chat. Not at Calc View, just at Calc Chat. Then any of the odds, 35 to 55, going on to the next page. All those are at Calc Chat, 41's at Calc View. Do any of the odds 57 to 63, they're all at Calc Chat, 59's at Calc View. Do any of the odds 65 to 71, they're all at Calc Chat, 65's at Calc View. Do any of the odds 73 to 83, they're all at Calc Chat, 77's at Calc View. Do either 85 or 87, they're both at Calc Chat, 85's at Calc View. Do either 89 or 91, they're both at Calc Chat. Do either 93 or 95, they're both at Calc Chat. 93 is at Calc View. Do 97, it's the only one like that. 99 is the only one like that. They're both at Calc Chat. 101 you can explore doing. It's up to you whether you do it or not, but that should be at Calc Chat. Depreciation, that's my brother and I were just talking over the weekend about taxes for the farm, and your equipment depreciates. And so he was showing me what he did on his taxes, so if we want to use that same type thing on ours because we're sharing the farm. So that's a very practical problem, so to speak. It should be at Calc Chat. 105s should be at Calc Chat. 107 is a graphical analysis, so you can do that if you'd like. It may be that's going to be a bit complicated. If you don't have a graphing utility, you may want to consider skipping that one. But try it if you can. Rewriting integrals, that's 109. That should be at Calc Chat. 111 should be at Calc Chat. It's a probability problem. Now, this is another thing that gripes me a little bit. I like this author. I like what his resources are, but he loves some more courses than this one and more books than this one. He loves to put new concepts in the exercises, not in the regular section where it seems like they should go, but in the exercises themselves. So if you want to take a look at that, you can. That's problem 111. I think he gives you ahead of that everything you need to do that. Then there's some true false. Any of the odds 113 to 117, you can do those if you'd like. They should be at Calc Chat. 119 should be at Calc Chat. Rewriting an integral, and 121 is a proof. If you're interested in doing proofs, you can certainly do that. The Putnam Challenge are always very difficult problems. I'll let you decide whether you want to do that. Any questions on 5.5? All right. Let's now move to, if you remember that little statement, sometimes integration is very, very hard to do. Therefore, if you can use something like even and oddness to simplify things, simplify. Well, here we're going to hit some forms that are indeterminate, and you would think, how can you do those? Well, there are some ways. So what I'm going to do is get out of this, and we're going to lose the screen share, I think, because I'm going to lose this one and go to pick up a new share, and that will be 5.6. I think this is it. Yep, that looks like it. Well, there we go. From current slide. Well, yeah, do you see this slide now? Integration? Yay or nay?
Yes.
Okay, so let me get this taskbar out of the way. You can't see, but it's in my way. So I'm going to scroll it way down here. Okay, and let's start. Chapter 5 is still integration. I have to click on the screen before it'll advance. Okay, 5.6 is indeterminate forms, and how we do this is a rule called L'Hôpital's rule. It looks like the hospital's rule. It's not quite right. I think he's French. I believe he was, and there's no S in there, so it's L'Hôpital's rule. Now, there's an interesting story about L'Hôpital, and I'll wait a page or two to get to it. But let's move on, okay? Objectives here are to recognize limits that produce indeterminate forms, okay? You may have a definite integral. It has limits, but you wind up with an indeterminate form, okay? Now, what we'll find out is sometimes using L'Hôpital's rule gives you a way to evaluate the limit, even though it looks impossible when you first look at it. Now, actually, this is not integration. I'm sorry, I was saying definite integrals. This is going back to limits, okay? So it seems like to me, why didn't they do this when they were doing limits? But they wanted you to get used to doing the other things and then introduce this, I guess. So what do we mean by indeterminate forms? We know that the form 0 over 0 is indeterminate. 15 over 0 is not indeterminate. That's just not defined, okay? Negative 7/3 over 0, not defined. Negative pi fifths over 0, not defined. You can't ever divide anything but 0 except maybe 0. That could be, sometimes it might work, sometimes it doesn't. We call that indeterminate. Now, what if you had something really weird like infinity over infinity? Which infinity is greater? We don't know. If they're on the same order, that may be 1. If the top infinity is way bigger than the bottom infinity, which doesn't make any sense, but it really does in a sense, then it's infinite, okay? But if the top infinity is a slower growing infinity than the lower infinity, then that may be 0. That limit may be 0. So we don't know, okay? Those are indeterminate because they do not guarantee that a limit exists, nor when they indicate what that limit is, okay, if one does exist. Excuse me. I'm going to have to, I'll try something with carbonation in it. Dr. Pepper, by the way. I think here's the problem, folks. This weekend I was working, like I said, on the farm, and the half day on Friday, it was one really dusty half day of work. So we drove over in the morning, worked in the afternoon. All day Saturday was a very dusty event. Well, most of it was anyway. Part of it was spraying some herbicides, which again wasn't a very pleasant experience. You tried not to breathe any of it, but it still was. You're out there in the stuff. And then yesterday, I had to do some mowing, which was another really, really dusty. And everything was there. There was straw, there was grass clippings, there were everything blowing into the air. So I'm kind of congested now, and that's probably why my throat's sort of going and coming on me. But anyway, sorry about that. So when you hit some of these forms and you don't know what it is, even if a limit exists, when you encountered one of those indeterminate forms, you attempted to rewrite the expression using various algebraic techniques. So for instance, if you could factor out that source of the zero in the denominator, then that limit may exist, right? So this was an indeterminate form. But this you could factor as 2 times x squared minus 1. Well, x squared minus 1 is x plus 1 times x minus 1. The x plus 1's go out. The limit as x goes to negative 1. Suddenly it has a value, okay? Because the denominator disappeared. So 2 times x minus 1, that would be as x goes to negative 1, this would be a negative 1 minus 1, but it'd be negative 2 times 2 is negative 4. Okay, now this one, the limit as x goes to infinity of this thing, what you do in that case is divide numerator and denominator by x squared. This becomes 3 over 2. This becomes minus 1 over x squared over 1 plus 1 over x squared. But who cares? Those are both going to 0, so this has a limit of 3/2. Okay? So sometimes the limit exists even when you first look at it. You say that's a 0 over 0, indeterminate. Infinity over infinity, that's indeterminate. But if you do the processes to them that you can do, legal steps, and simplify that, especially that denominator, that's where you want to get rid of those things. Now, with infinity over infinity, you need to get rid of them in both. But here, you need to get rid of the 0 in the denominator. If you can do that, you can evaluate the limit sometimes. Still not valued there, but you can evaluate the limit there. Occasionally, you can extend those algebraic techniques to find limits of transcendental functions, okay? For instance, this one, e to the 2x minus 1 over e to the x minus 1. Well, when x is approaching 0, 2 times 0 is 0, e to the 0 is 1, this is 1 minus 1. That's 0 over e to the 0 is 1, 1 minus 1 is 0, 0 over 0. Another indeterminate form, but this could be written as e to the x squared minus 1, and this is over e to the x minus 1. This is e to the x plus 1 times e to the x minus 1. This cancels the second one out. You get e to the x plus 1, and as x goes to 0, that would be 1. Plus 1 is equal to 2. And that's exactly what they did here. The numerator factors in e x plus 1 times e to the x minus 1. The denominator is e to the x minus 1. These two divide away to be 1. And this gives you the limit as x goes to 0 of e to the x plus 1. E to the 0 plus 1 would be 1 plus 1 is 2. There that one is. All right. Excuse me again. I can almost taste the dust. Okay. Not all indeterminate forms, however, can be evaluated by algebraic manipulation. It'd be great if they could, but they can't. This is often true both When algebraic and transcendental functions are involved, both of them that you can't really fiddle with too much. For instance, here's the limit as x approaches 0 of e to the 2x minus 1. Same thing we had before in our numerator, but now the denominator is just x, okay? As x approaches 0, this 2 times 0 is 0, e to the 0 is 1, 1 minus 1 is 0 over 0, indeterminate. But there's no algebraic way to simplify this. They tried one. They tried, well, let's just split the numerator over the denominator separately. E to the 2x over x minus 1 over x. Okay? Well, e to the 2x, as x goes to 0, that would be 1 over 0. That would be infinity. Okay? In other words, undefined. That wouldn't even be infinity. That would be undefined. Okay? And this would be undefined. So now you've got two completely undefined rules and no way to do that. What is undefined minus undefined? That's pretty undefined, isn't it? Okay. Now, of course, you could use technology to estimate the limit, as shown in this table here. Here's the example as if you use your graphing device, whatever you have, program or calculator or whatever, to evaluate this, you'll see that it has a hole in the graph there. The reason it has a hole in the graph, because this is not defined when x equals 0. But the limit obviously is equal to 2, okay, graphically. Now the question is, do you always want to graph your, especially these very complicated looking expressions, and see if you can figure out what the limit is? Frankly, I don't. So let's see if there might be a better way. Okay, well, you could set up a table. Okay, this does the same thing. This is how you would do your graph. Plug in different values and see what they are heading to. And as x is approaching 0 from the left-hand side, from minus 1 to minus 0.1 to minus 0.01 to minus 0.001, you see you're going, here it would be 0.865, here it would be 1.813, this would be 1.980, up to, they took it all the way to, 1.998. Sorry, clogging up again. Going back the other way, plug at 1, then at 1/10, you go from 6.389, 2.214, 0.01 would be 2.020, 0.001 would be 2.002. This one's approaching 2, that's approaching 2. I don't see any way it can help but be 2. But that's a lot of calculations here to get one solution. So hopefully there's a better way than that. Okay? And that's where L'Hopital's rule comes in. All right. I don't think they do the little blurb on them. No. Okay. So let's talk about the little blurb. Guillaume, that's the French word for William, Guillaume L'Hopital. He lived, if you've been keeping up with timelines, 1661 to 1704. I guess a little part of his life probably did overlap Newton's a little bit, but he was very, very young, so I doubt if he ever met or knew Newton. But some of the people who followed Newton, that extended calculus and followed Leibniz as well, and extended him, and since Leibniz was German and L'Hopital French, well, there were others involved. One very famous family was the family of the Bernoullis. They were brilliant minds. There were two brothers. They call them John. It was Johann and Jacob and John Bernoulli. They were both brilliant mathematicians and good physicists too, and they competed with each other like crazy. They entered contests to beat one another. It was very competitive family. And then they each had sons, if I'm not mistaken. Probably, I think one has at least one daughter too. And several of those kids were incredibly bright in mathematics and physics as well. And some of them followed in their father's footsteps and were also very difficult people and very competitive. I remember the story of one son entering the same contest his father did. His father was used to winning, very used to winning. He thought he was going to pocket that, whatever it was, let's just say $700 or $7,000 or whatever the prize was. He just knew he was going to get it, but he got beat that year. And when he found out it was his son that beat him, he kicked him out of the house. Okay, so I mean, they were a very competitive family, brilliant mathematicians, and also not that easy to get along with. And L'Hopital studied under Johann Bernoulli. Bernoulli, I think the whole clan of them were from Switzerland, but they moved all over Europe and taught all over in Europe because they were a very, very bright family. But what L'Hopital was good for was taking the complicated mathematics that he was learning from these brilliant minds and simplifying them into textbooks and things like that. And he wrote probably one of the first textbooks. It says here, L'Hopital is credited with writing the first text on differential calculus in 1696. And in that text, he wrote something that he learned, and he acknowledged that it came from him, from John Bernoulli. But that was L'Hopital's rule. Everybody picked up on it. They've ignored the citation. They ignored where he gave credit to Bernoulli. They call it L'Hopital's rule because it was such a handy, handy rule. And repeatedly he said, no, it's not mine. It came from Professor Bernoulli's. And Bernoulli was very angry that they gave him credit, but he knew, I think in his heart of hearts, that it wasn't L'Hopital's fault. But anyway, you can read more about it. That can be a paper topic. Just this thing right here in the book can't be your source. You have to go to an outside source to get that. So here's L'Hopital's rule. To find the limit illustrated that we just were talking about, this one right here, y is equal to e to the 2x minus 1 over x, that none of our other methods will work. There's not an algebraic simplification. There you have either a graphical or a tabular thing to indicate there must be a limit. Here's what L'Hopital's rule does. It doesn't have you graph a thing. This theorem states that under certain conditions, we'll get those conditions, the limit of the quotient, f of x divided by g of x, that's it right there, f of x divided by g of x. If that is an indeterminate form, the limit of that quotient is determined by the limit of the quotient of the derivatives. So if you can't calculate the limit based on this, take a derivative of the numerator, take a derivative of the denominator. Now it's not clear why that's true, but do it, see if that limit exists. And to prove this theorem, you may use a more general result called the extended mean value theorem. So we're not to L'Hopital's rule yet, but here's what it is. The extended mean value theorem, if f, and my guess is this is what he learned from John Bernoulli, if f and g are both differentiable on some open interval a to b, both f and g are, and they're continuous on that interval from a to b. Now here they're differentiable on the open interval, but they're continuous on the closed interval, including the endpoints, such that g prime of x is not equal to 0. That second function, g, is differentiable, but not equal to 0 for any x on that interval from a to b. Then there does exist some point c on that interval a to b such that f prime of c over f g prime of c is equal to f of b minus f of a over g of b minus g of b, g of a. Now, sorry, this is getting very, very difficult to talk. Let me try something. Okay. I don't know if that's any better or not, but let's try it. And basically, remember the mean value. If you just did this numerator, that made sense on the mean value theorem. Just did the denominator, that makes sense on the mean value theorem. But this says, as long as these conditions are met, that it's the same C. You can use the same C and make that happen. Now, that's not entirely clear to me why you can make that assumption, but they're saying you can. Or, more precisely, if there is a point, well, if all these others are met, then there has to be some point where that's going to be the case. And therefore, let's go on to L'Hopital's rule. Here's the theorem, that's L'Hopital's rule. That was theorem 517, here's 518. If f and g are functions, they're both differentiable on that open interval a to b, and that interval contains c, except possibly at c itself. At c, that may not be differentiable, but everywhere else it is differentiable. Assume that g prime is not 0, that has to be the case, for all x's in that a to b. Okay? So if it has just one 0 or a dozen zeros in that interval a to b, this is out. Okay? Except, again, possibly at c itself. Okay? If g prime of 0 at c, you may be okay. If the limit of f of x divided by g of x as x approaches that value c produces that indeterminate form of 0 over 0, then the limit as x approaches c of f of x over g of x, which we saw was a 0 over 0, is going to be the same as the limit of, as x approaches c, of f prime of x over g prime of x. And you can easily imagine some functions whose limit may be 0 at x approaches c, but whose derivatives may not be 0 as x approaches c. If that limit exists, then, and even if it exists or is infinite, then that limit may exist. This result also applies when the limit of f of x over g of x as x approaches c produces any one of the following indeterminate forms. Infinity over infinity, woo. Minus infinity over infinity, okay. Infinity over minus infinity, either one of those produces a negative infinity over infinity. Or minus infinity over minus infinity, which is basically equivalent to infinity over infinity. If any of those limits were those, you can do L'Hopital's rule. So L'Hopital's rule can also be applied to one-sided limits. The limit may exist only going one direction, but not from the other direction. Okay? For example, the limit f of x over g of x as x approaches c from the right approaches the indeterminate form 0 over 0. Then you can still do this, but you have to keep the limit to being from the right only, provided that limit exists or is infinite. Okay, we'll get to the infinite part later. So, here's the problem, the very one that we're talking about. What is the limit as x approaches 0, e to the 2x minus 1, okay, e to the 2x minus 1 over x, okay? As x approaches 0, 2x approaches 0, e to the 0 approaches 1, 1 minus 1 is 0 over 0, can't evaluate it. Indeterminate, okay. Now if that had been 17 over 0, yeah, that's no good. You might still pursue L'Hopital's rule because remember that limit could be Nope, they didn't include infinity over, they just said infinity. So I don't think you could still do it then, okay? So, what does L'Hopital's rule say we can do? Take the derivative of the numerator. Y'all want to see this on whiteboard first? Yay or nay?
Yeah.
Yes, okay. So let's go to, oh, come on back. Go to the whiteboard. All right, can I erase? Yeah, this is back where it's in the way again. You can't see this, but this taskbar is smack in the way. Okay. Do y'all need the previous problem any longer? I don't hear anything, so I'm going to erase. Okay? So here's our example. Let me get my book in my lap so I don't have to turn away as much. The limit, this is going to be a little tedious. What we're looking for is the limit as x approaches 0 of e to the 2x minus 1, it's on the same line with the e, over x. Now, what was our first approach to ever finding a limit? Plug it in, see what you get. And like I said, when you plug in x equals 0 here, you get 2 times 0 is 0. E to the 0 is 1. 1 minus 1 is 0. Your denominator as x goes to 0 is 0. Indeterminate. But what L'Hopital's rule says, that's the same as the limit ugly m as x approaches 0. Always going to the same limit, by the way. Goodness, that's ugly. Of, what's the derivative of e to the 2x minus 1? Anyone want to hazard a guess? Well, you know, the derivative of an exponential function is itself, e to the 2x. But this, since the argument is also a function, you take the chain rule, and the derivative of 2x is simply 2. Okay? And then derivative of minus 1 is 0. Okay? And then the derivative of x is simply 1. So, what is the limit? If I could get this right. Goodness gracious, I'm having trouble even focusing. The limit as x approaches 0, always the same limit here. The other thing is, up to this past weekend, I'm very, very tired. So that's another issue here. My eyes, especially when this tedious writing on the screen, is making them ache from the core. All right, what's the limit of this as x approaches 0? Well, 2 times 0 again is 0. E to the 0 again is 1. 2 times 1 is 2 over 1, which is just 2. Oh. That's equal to 2. So that does have a limit. Even though the original form can't be done anything with algebraic simplifications, anything else, do L'Hopital's rule. Take the derivative of the numerator and denominator, try again. See if the limit exists. If it does, you found the limit for your problem. Okay? And that's, any questions on that before we go back to the book? All right. I hear no questions, so
No.
okay. 5, 6, and go back to the current slide. Okay, so now I've got the big box, but you say this doesn't block. The little box blocks, this one doesn't. So let's go on. What's that limit? Doesn't exist. I mean, it's indeterminate form. Direct substitution results in indeterminate form because the numerator goes to 0, the denominator goes to 0, 0 over 0, indeterminate. 7 over 0 would have been doesn't exist, don't go any further. You can't do it, okay? But 0 over 0, indeterminate, keep trying. All right. But you can apply L'Hopital's rule, shown here. Basically, we did it, but I didn't write it down this way. Derivative of e to the 2x is e to the 2x times 2, chain rule, minus 0, over derivative of x, that's 1. So this would be the limit as the derivative of this, again, was 2 times e to the 2x divided by 1. Sorry. All this water I'm drinking, we may have a pit stop later, but that's the other thing. I'm probably very, very dry from the weekend because it was a beautiful weekend, but the wind was blowing, low humidity out there in the dust and everything else. I know I was sweating, but not feeling like I was sweating because the water was evaporating it just as soon as it went. So I got very dried out. And I think that's what you're hearing now, and that's why I'm having trouble breathing. Okay, so anyway, this is the derivative of the numerator divided by the derivative of the denominator. Now you can take that limit, let x approach 0, e to x is 0, e to the 0 is 1, 2 over 1 is 2. That is your limit. L'Hopital's rule allows you to do that. Any questions on that? That was example 1 in 5.6. Now, another form of L'Hopital's rule states that if the limit as f over g as x approaches infinity or negative infinity produces an indeterminate form of either 0 over 0 or infinity over infinity, then you can do the same thing. Continue and do the limit as x approaches either plus or minus infinity, whichever it's doing, as f of x over g of x is the same as the limit as x approaches that infinity, whichever one it is, of the derivative of f divided by the derivative of g, provided that those limits on the right do exist. Okay? And remember, that would also imply that g prime can't be 0 for anywhere on the interval, with a certain exception we'll get to a little bit later. Okay? So here's what we've got now. Oh, do you want to see this on whiteboard or just do it here? Let me know.
Whiteboard, please.
Whiteboard, okay? All right. All right, to clear this one? Okay. Now we have the limit. And I'm hoping that rectangle is not going to be in the way on the whiteboard either. It's the limit as x approaches infinity This is really going to be fun. It's not too bad. Okay. Of log x over x. Can you see that log x, or is that block in the way? Or more importantly,
I can see you writing it.
Okay, and you can see the over x there too. No problem.
Right.
Okay, it's not fading in and out. It's fine. Okay. All right, so what would we do here? The limit as x goes to infinity. Well, now, one thing you can do is picture this. Log of x, if you remember, log of x is not defined at x equals 0. Okay, so it's approaching the y-axis asymptotically, but getting very, very negative the closer it gets to 0, but cannot equal 0. Never can equal anything negative. Okay, natural log will approach here. When it's going up from here, it's approaching 0. When x is equal to 0, log x is 1. Log of 0 is 1. Log of, I'm sorry, you can't do log of 0. Log of 1 is 0. Okay, that's what I meant to say. Log of 1 is 0. Log of 1/2 would be a negative number. Log of 1/10 would be a more negative number. And the closer you get to 0 with the x, the more negative it becomes. So it's a vertical asymptote there, x equals 0. But when x is equal to 1, log is 0. But then anything beyond that, log is a gradually increasing function, never decreases, but doesn't increase as fast as it did a while ago. Gradually increasing, but slopes off. You can picture, it's not the same, but it's very similar to a square root function. Square root function goes up here and never levels off, always is increasing, but doesn't have a limit. Okay, so log x, same way. At x equal 1, it's 0, and anything past that is increasingly positive and just keeps increasing. So that's what log x does as x goes to infinity. Log x is going to infinity. Now picture also on the graph the identity function. Alpha of x equal x, okay? It crosses at 0 and goes up at the 45-degree angle into the first quadrant. It's going to infinity as x approaches 0, okay? I'm sorry, as x approaches infinity, it's going to infinity. Now, here's the kicker. It's going there faster than the log function. Remember, the log function is a decreasing increase, whereas a identity function is a constant increase, okay? So you might get the idea that the log x is going to infinity more slowly than x is, and indeed that's right, so therefore that may not be indeterminate any longer. But that's just a general view of it. Let's do what L'Hopital's rule says. Let's take the derivative of the numerator and the denominator, and that would be the limit. Now, I can't see all of what I'm writing because that box is in my way. The limit as x approaches infinity, and that bar was not there, the pen just put it there. Okay, x approaches infinity of, now what's the derivative of log x? Anyone remember that? Please say yes. Derivative,
X.
say again?
1 over x.
1 over x, perfect. And then what's the derivative of x? Pretty easy. 1, right? d by dx of dx is, dx dx is 1, okay? So what's this? If I could get that to go out of the way, because I can't even see where to write my equals. There it is, okay. You can't tell what's in the way probably. That's equal to 1 over x, and as x goes to infinity, 1 over infinity is going to 0. So that limit, sure enough, is 0. Undefined, going infinitely large, over infinitely large, the thing is the top infinitely large is slower than the upper infinite large, so the upper one wins. It's going to infinity much, much faster than the lower one does, so the ratio of those two would be 0. And that's what they get in the book too. All right, to go back to it, Okay, if I can. There we go.
Yeah.
Was there a question?
No.
Okay. So let's see how the book does it. But direct substitution, plug them in, you get infinity over infinity. Well, yeah, that's what this says. However, applying L'Hopital's rule, you get 1 over x over 1, which is simply 1 over x. Let that go to infinity. 1 over an infinitely large number is getting closer and closer to 0. Okay? Okay. Now, so L'Hopital's rule works in both of those circumstances. Let's see if they do example 3. No, they don't. They skip example 3. So this is definitely a whiteboard problem, right? So let's get my whiteboard back up again. All right, to erase the previous. Yay? All right. Let's do example, example 3. Top of page 348 if you have the book. Or even if you don't have the book, it's still there. Okay. So here's the limit. A little more complicated. Of course, they do the simple ones for you on the slide set. Now, okay. My pen was deciding not to write, but finally it did. So there's the limit as x approaches negative infinity. Pretty ugly, but I guess it made it. Goodness, my eyes hurt. This strain is just driving them nuts. I don't know. Both days when I came in from working outside, they were almost bloodshot. There was so much dust had gotten in them. They look better this morning, but they feel just about as bad. Okay, so there's the limit of x squared over e to the minus x. Of x squared over e to the minus x. I can't write. Let me see if I can erase that and do it better. The writing with the keypad is a challenge because sometimes it seems like my finger sticks. I'll pull it across, but it's sort of like it hangs up somewhere. E to the minus x. So let's see if I can get there. That went more smoothly that time. Okay, there it is. Now, when I first was doing this, I said, that's not even a L'Hopital's rule problem. And then I realized it's e to the minus x infinity here. Okay, when x gets very, very, very negative, infinitely negative, and you're squaring it, that's going infinitely positive, right? 1 over a very large negative number squared is a very large positive number. Let's take one that's not too big, like negative 10. Negative 10 squared would be positive 100. Negative 100 squared would be positive 10,000, okay? Negative 1,000 squared would be positive 1 million. I mean, it's going up there, folks, okay, really big, okay? Now, e to the minus x as x goes to infinity. If you think about it, e to the x, positive x, it starts near 0 when x equals 0, e is 1, and from there on it's going up. But e to the minus x starts up, comes down and passes the x equals 0, 1, and then approaches positive infinity as it goes up, approaches 0 as x goes to positive infinity. So that's what we're talking about here, e to the minus x. What's it doing? It's going way positive too. Now the question is, who wins? Frankly, exponential functions usually beat polynomials, okay, in getting out of hand really quickly. That would be my gut response, would be this is going somewhere close to 0. Yeah, but let's see what they get. Well, let's try plugging them in. X to the minus infinity squared is going to be an infinitely large number. And as x goes to minus infinity, this is minus of minus infinity, which is e to an infinitely large number. That's going to be infinitely large. Way, way infinitely large. Okay? And I think that's going to win. But let's use L'Hopital's rule. And that says that if that comes out being an infinity over infinity as x is going to either plus or minus infinity, then we can do the limit again. But this time take the limit, again of the same value as x approaches, goodness, this is rough on the eyes, negative infinity. Okay, that's a pretty ugly negative infinity. Here's the other issue here. I'm left-handed, but I'm having to hold the button down with my left hand, so I'm drawing with my right hand, and that is not my good strong hand to be writing with. So let's take the derivative of the numerator. What is the derivative of the numerator? Anybody? Derivative of x squared is 2x. Well, let's take the derivative of the denominator. Well, derivative of an exponential function is the same exponential function, e to the minus x, but chain rule says you put another minus in front. Okay, so now let's take that as x goes to negative infinity. Well, 2 times the negative infinity is going to be negative infinity. Oops, negative infinity. Okay, as x goes to negative infinity, 2 times negative infinity is still going to negative infinity. Twice as fast, but it's going there. Okay, minus e to the minus x. Remember, e to the minus x is going to positive infinity. You negate that, it's going to negative infinity too. Hey, we're back same place we were before, only rather than positive infinities here, they're negative infinities there. But because they're both negative infinity, we can do L'Hopital's rule again. So let's do it again and take the limit as x approaches negative infinity. Goodness, this is tedious. That's an ugly infinity. Just assume that's an infinity there. Good old right hand getting tired. Okay, now let's take the derivative again. What do we have here? Derivative of that is 2. Derivative of 2x is 2. That's the numerator. The denominator going to be a minus e to the minus x times another minus, and that's going to be back to being e to the minus x. Okay? Because when you take the derivative of this, you keep the minus sign. Okay? Derivative of e to the minus x is e to the minus x. But then you do chain rule and take the derivative of minus x, and that's another minus sign, and one minus sign cancels the other out and makes it positive. Okay, so it's e to the minus x. Now, let's take the limit as x goes to negative infinity. That's going to be 2 in the numerator. I can do that one. Okay, that's going to be 2. Okay, and in the denominator, again, when x is going to negative infinity, e to the minus x is going to positive infinity, which sure enough is going to zero. because any little number 2, how big? 200, 2 million, it doesn't matter, divided by an infinitely large number, ultimately is going to 0. Closer and closer and closer to 0. Okay, that was our example 4, that was our example 3, top half of page 348. Okay. All right. Any questions on that one? That's not in the book, but the next one is. So I'm going to, or the next statement is anyway. So let's go back to the book, 5.6. Okay, and we'll go from current slide. Okay. That was example 2. Then we did example 3. And before we get to example 4, here was the verbiage just about the middle of page 348. In addition to forms such as 0 over 0, indeterminate, or infinity over infinity, also indeterminate, there are other indeterminate forms such as 0 times infinity. Who wins there? 0, which is usually anything by 0 is 0. But what if infinity is a big enough number to yank that along? I don't know. 1 to the infinite, that looks like that would be 1 to me, but I don't know. Infinity raised to the 0th power, seems like to me that should be 1, but I don't know. Let's see. Or 0 to the 0th power. Now that makes no sense whatsoever. Okay? And infinity minus infinity. Yeah, who wins that one? Which infinity is bigger? Okay, we don't know. For example, consider the following 4 limits that lead to indeterminate forms 0. Goodness, I don't know what to drink next. I'm going to try Dr. Pepper again. It seems like neither one of them do any good, but I think my wife would say, you should have taken an antihistamine. But if I took one now, I'd be asleep in an hour. I guarantee you. Okay. I don't handle those well. So let's consider an example of following 4 limits that lead to the indeterminate form 0 times infinity. Who wins here? So this is the limit as x goes to 0 of 1 over x times x. Okay. It doesn't take much to see. Well, of course, 1 over x as x goes to 0, that's an infinitely large number. That I say is undefined, okay? Infinitely large number. Limit as x goes to 0 of x, of course, is 0, okay? But this is real simple to do algebraically. Just write this as x over x is 1. So the limit of that is 1. It doesn't matter, okay? It's sort of stupid to talk about the limit as x is going to infinity of 1. It doesn't matter. I mean, is x going to 0 of 1? 1 is 1 is 1 is 1. Okay. Now, this one, 2 over x times x, this still is going to 0. No, this is going to infinity. This is going to 0, so it's actually infinity times 0 is what they're saying. It doesn't matter, but it's pretty obvious here. The x's would cancel out, and you would leave with 2 over 1. So that one would be 2. Now this one, I think we just saw, if we didn't see it, we would, if we had done it. This limit is 0, because this is going to 0 as x goes to infinity. This is going to 0 to, Let me state that again. The limit as x is going to infinity of 1 over e to the x. So e to the x is going infinitely large, and as x is going to infinity, that's really going to infinity. So that's 1 over infinity is 0. And then x going to infinity, of course, is going to infinity. Well, what would that tell you about x over e to the x? Well, L'Hopital's rule says, do it. I mean, why write them in this form when you can either evaluate them algebraically or use L'Hopital's rule? Which, of course, you can here. If you wrote this as x over e to the x, then that would be an indeterminate form. Well, that would be infinity over infinity, as x going to infinity, which would be one that we've already talked about in indeterminate form. Take a derivative of the numerator, you get 1. Derivative of the denominator would be e to the x. Who wins there? As x goes to infinity, 1 over that is 0. Okay. Now, flip those over. 1 over x is still going to infinity. E to the minus x is going to okay, I'm sorry. 1 over x is going to 0, and e to the x, as x goes to infinity, is going to infinity. So this, again, is one of those forms. What if you wrote e to the x over x? Okay? L'Hopital's rule, that's infinity over infinity. Derivative of e to the x is e to the x. Derivative of x is 1. What's the limit? Is x goes to infinity of e to the x? Infinite. So, again, these are sort of stupid examples, but they're showing you can't always tell what happens to 0 times infinity. These that are obvious, yeah, you can figure out what they're going to be. But what if it's not so obvious? What do you do then? Okay? Does L'Hopital's rule still work? We just did it in these. Some of the others you can still make it work. Because each limit is different, it's clear that the form 0 times infinity is indeterminate in the sense that it does not determine the value or even the existence of a limit. Basically, you attempt to convert each of those forms to a 0 over 0 or infinity over infinity so that L'Hopital's rule can be applied. And that's what I was doing. I was saying, why write it like this? Get it in L'Hopital's form, and you can go to town with it. Okay, so here's one. All right. I am going to make a guess y'all want to go to the screen, right? Whiteboard. All right, to erase. I assume so. Okay. Here's example 4. The limit as x approaches infinity ugly infinity. God, everything is so dry. Nose is itching like crazy. Of e to the minus x and to me these are sort of stupid examples. I guess I've said that a dozen times now. Times the square root of x. Now, if you take it literally, sure enough, as x goes to infinity, e to the minus x is going like that, that's going to 0. Okay, e to the minus x starts really large for negative values. A minus times a minus is a positive, e to the positive value is extremely positive, and it goes down when x equals 0, it's 1, and then when x gets very large positive, that's going like this. So that's going to 0. Square root of x, of course, is going, as x goes to infinity, that's going infinitely large. So that would be a 0 times. Why even refer to it in that form? Let's just rewrite this in something we can do. And I don't even know why to mention that the times. That doesn't make any sense anyway. Just rewrite this as the limit as x goes to infinity. That doesn't change. Not in this problem anyway. Of the square root of x, that's in the numerator, divided by e to the x. Okay. Now, that's say, as x is going to infinity, square root of x is going to infinity, e to the x is really going to infinity. So I can just look at this and almost guarantee you that's going to 0. Because e to the x goes to infinity much faster than square root of x does. Okay, they both go to infinity. E to the x gets there much quicker. Goes way faster. Okay, but let's do it. L'Hopital's rule, that fits L'Hopital's rule, infinity over infinity. We can certainly do that. So let's take the limit. Well, yeah, the limit as x is going to infinity. This is the tedious part of all this, is writing all this mess over and over again. Okay, of, let's take the derivative. Now, if you've been in my class long enough, you probably know I don't like taking derivatives of radicals. How would you write this before you would take a derivative of it? X to the what? Okay, x to the 1/2 power. Okay, it's pretty crowded there. Okay, what's the derivative of x to the 1/2? That would be 1/2. Thinking of what I'm going to write next and wrote it rather than what I said I was going to write. Okay.
1/2 to the x of 1/2.
Okay, you're right. 1/2 times x to the what? Negative 1/2? Okay, I'm sorry, I'm too near the top, so I'm dragging it down. Sorry, this is ugly. Okay, that's 1/2 x to the minus 1/2 over, and derivative of e to the x is still e to the x, right? Okay, now, let's evaluate that limit. 1/2, that's 1/2. We won't worry about that now. You could take that outside the limit if you wanted to. 1 over the square root of x, as x goes to infinity, that's going to 0. Okay? And then you get 0 divided by an infinitely large number. And that's going to 0, okay? So there's no way that this isn't going to 0. Okay. Because now you have in the denominator a 2, which is just a 2, a square root of x, which is the square root of x, and an e to the x. All those, the 2 with x in it, are going to infinity. 2 is just 2. It's going there twice as fast, but it's just going there. So yeah, 1 over infinity is 0. All right, and that's what they get in the book as well. Sorry. Now, okay. They do make a little, sorry. All right, to leave this and go back to the PowerPoint. I forgot I wasn't on the PowerPoint. Okay. Go back to current slide. Okay, there was example 4. Now, I think they do the same thing we did, because direct substitution produces a stupid expression, okay? Let's rewrite it, and certainly that makes sense. And they chose to rewrite it just like we did, as square root of x over e to the x, which of course is, as x goes to infinity, square root of x is going to infinity, but slowly, and e to the x is going to infinity, but incredibly rapidly, okay? Both of them going to infinity, though, so it's infinity over infinity. So then let's do L'Hopital's rule, which is, they write it slightly differently. I said that you did 1/2 over the square root of x. 1/2 x to the minus 1/2 over e to the x. And when they rewrote that, the 2's in the denominator, radical x is in the denominator, and e to the x is in the denominator. All you got in the numerator is 1. So this is a numerical number, 1, divided by 2, which is just a number. But this is going to infinity, that's going to infinity really, really rapidly. So 1 over an infinite number is 0. Okay. And 1 over 2 times an infinite number is 0. Okay. So that's going to 0. Now, this is the top. No. Yeah, this is the top part of 349. But they do say something else above this. It says when rewriting a limit in one of the forms 0 over 0, infinity over infinity, does not seem to work, try the other form. So for instance, on that last problem, what if you had done this one and put this in the numerator, and this is 1 over the square root of x in the denominator, which seems like a stupid thing to do, but I mean, you could do it. E to the minus x in the numerator, and you put in square root of x in the denominator, which would be effectively x to the minus 1/2. Okay? Minus 1/2 because we moved it downstairs. Okay? Now, what's the limit of that as x is going to infinity? Well, the numerator, as we said before, is going to 0 because e to the minus x as x is going to infinity gets closer and closer to 0. Okay? 1 over the square root of x is also going to 0. So don't go with those two functions. I mean, you could. That'd be 0 over 0 if you went that way. Now, please look at the book and follow this. If you take a derivative of those, though, even though 0 over 0 may be a little more appealing to you than infinity over infinity, when you take derivative of those, e to the minus x is just going to be minus e to the minus x. Okay, but derivative of the square root of x, or 1 over the square root of x, if you put that down, the x to the minus 1/2. Derivative of that would be minus 1/2 times x to the minus 3/2. And the limit of that as x goes to infinity is still going to be 0. So there's no way you're ever, in fact, in the numerator it was a minus 0, and the denominator is a positive 0. So you almost want to say the cows are going to, I was using an agriculture example, they're both going in opposite directions, but your coefficient is getting worse in the denominator, and that is not going to be something. And like they show here in the book, if you did it, your denominator keeps being a 0 over 0 because the numerator is just back and forth between minus e to the minus x and e to the minus x. That's still going to be a positive or negative infinity. Your denominator is also keeps getting more and more because you take the derivative of x to the 1/2 or negative 1/2, you get negative 1/2 x to the minus 3/2. Take the derivative of that, you get positive 3/4 times x to the negative 5/2. It just keeps getting worse and worse and worse, and you never reach it. So if you wind up in a situation like that, then reverse them. Even if it's an infinity over infinity, it works better than something that never converges or never reaches a limit. So anyway, that was what was there. I don't know if it's worth saying, but I tried to say it. It's sort of awkward. Okay, so let's move back to where they picked off here. This is just above example 5 if you've got a book. The indeterminate forms, 1 to the infinity, they mention. Infinity to the 0, they mention. And 0 to the 0, which they arise from limits of functions that have variable bases and variable exponents, which is a strange situation. Okay? But let's see what we can do with them. Here's example 5. I'm sort of guessing this might be something you want to do on the whiteboard. Is that right? Okay. My cursor sometimes disappears and it's hard to follow. Okay. Let me clear this one out of the way. Now, this is a rather bizarre looking problem, but if you're at all familiar with it, you probably can give me the answer, okay? But you may not be, so let's write it down. Okay. I think all the fiddling I did before, I changed this, so let me, okay, I think that's better. Maybe. Okay. This is the limit. Again, sometimes the cursor just sticks. It doesn't do anything. The limit as x approaches infinity so as x is infinitely large of 1 plus 1 over x. This is an ugly x. That's a terrible looking x. Raised to the x power. That x hopefully will come out a little better. Yeah, that came out better. Okay. Now, that's an awful looking form, isn't it? That's so ugly, I can't tolerate it. So I look at that and say, what in the world? It looks like a stick man that fell down. Okay. Let's see if we can wipe him out. Okay. That's a little bit better. Okay. Now, here's how the book approaches this one. I want to say, does anyone recognize what this is going to turn out being? If not, it's okay. But if anyone is familiar with it, it's going to be a fairly simple answer, but it's not simple how to get there. What they say first is let's just set this equal to some number y. And that's what we're looking for. Keep that in mind. We're looking for y. That's the thing we're looking for. Not x, but y. Now, why would we say that? Because this is some number here. Okay? First, this is an indeterminate form. So this is, no, it isn't. That as x goes to infinity, this is going to 0, so this is 1 raised to an infinitely large power is what that is. Okay, and that's not real clear what 1 raised to an infinitely large power. On one hand, you might say, isn't that going to be 1? Because 1 squared is 1, 1 cubed is 1, 1 to the 17th is 1, 1 to the 500th is 1. Why wouldn't 1 to But this isn't quite 1. This is 1 and a fraction, depending how big or small the fraction is, that's the same degree of what this is going up to. So it's really hard to tell what this is going to turn out being, unless you're familiar with the form. So here's what we're going to do. Anytime that the complicating factor here is a power, how you undo an exponent is take a log. So that's what I'm going to do next, is I'm going to reverse the sides of these two, because they wrote it on the other side. I'm going to say the log of y is going to be, now here's where I run into some issues here, okay? And I don't want to do it, but I sort of have to. That would be the log of the limit, because y is equal to that limit, and the log of y would be the log of that limit. The limit as x goes to infinity. And this is what gets so tedious here, without having to write all this stuff over and over again, and it's hard enough to write the first time. Okay, that's supposed to be an infinity there. Of 1 plus 1 over x to the, ugly parentheses, to the x. Okay. This is getting, the writing's getting worse and worse because my hands are getting tighter and tighter. It was a rough weekend on them as well. They're stiff and sore. Okay. Now, what we're going to do now is reverse the order and take the limit of the log. Okay? And that is an okay thing to do. Because the natural logarithm function is continuous, you can reverse that order. Okay? And I don't want to get into all the theoretical reasons why you can, but that's all that's required. So the log y here would be the limit getting so tired of writing this thing. The limit as x approaches infinity it came out a little better of the log of this. Now this is taking so many steps, it's wearing me out. So I'm going to put this in bracket here. That would be the log of 1 plus 1 over x come on back, cursor. There you are. To the x. Okay. And now I'm going to close that bracket off. Okay, I'm sorry. Nothing is helping. My eyes, my hands, my throat, nothing. Maybe I should just take an antihistamine and go to sleep. I don't know. That would be fair to y'all, would it? Okay. Now, if you remember the rules for taking, I'm going to leave the log y alone. That's not going to change for a while. So, and that limit. Is it all right if I just put limit and not put the x going to, all that's going to stay the same. what I'm going to change here, a log of something raised to a power is the same as that power x times the log of 1 plus 1 over x. This is ugly, ugly writing, and it's okay. Now, and this limit is x goes to infinity. All right, now what do we have here? What they do next seems like a sleight of hand, but it is okay to do. It's sort of like what we're talking about at the top of the page. Try different forms. And rather than going through the agony of trying them and failing, and doing that while I'm writing with my right hand finger, which is terrible since I'm left-handed, if you rewrite this x as 1 over x, so that moves it downstairs. So I'm going to do this at one fell swoop. I'm rewriting x up here as 1 over x, because 1 divided by 1 over x, if you invert the 1 over x, that's just x. So we basically wiped it out up here, okay, which I could have used an eraser. That probably would have been better. Let me use that eraser. And, okay, wiped out those. All right. So this is the form. So what is this going to do? Remember, x is going to infinity, and as here we go again. As x is going to infinity, this thing is going to 0. 1 plus 0 is 1, and the log of 1 is 0. And as x is going to infinity, that's 0. So wow, we've got it down to a L'Hopital form. Believe it or not, we're there. Okay, so let's take a derivative. So this is then going to be, now can I get by without writing the limit there? Still, as x is going to infinity, don't forget that. I'm just going to write the limit part of, I'm going to write it big like this now. What's derivative of log of this thing? Derivative of a log is 1 over that thing, okay? 1 plus 1 over x. Well, let's rewrite that if we could. While we're here, among friends, okay? That's 1 over, now this thing right here would be x plus 1 over x. Do you see that? If you write that on least common number, 1 is the same as x over x plus 1 over x would be x plus 1 over x. Okay? Whoops, somebody's coming in. I can't see the oh, that's iPhone, which I assume is James again, unless we have another iPhone. James, is that you again? Or is that somebody else using an iPhone? James, is that you? Just came back in? Who is this?
Yes, sir.
It's James again?
Yes, sir.
Okay, good. Okay. Just want to make sure it was you, because somebody else could have had an iPhone too. Okay.
It was connecting, then it just shut out, so I had to rejoin.
Yeah. Sometimes that happens. I think maybe on phones worse than on computers, but yeah, it does happen. Okay, so here's what we got. Derivative of a log is 1 over the argument, right? What is the argument? That's x plus 1 over x. So it'd be 1 over x plus 1 over x, which basically would be x over x plus 1. Now, I'm skipping some steps here because it's so hard to write all these things in so many steps. So tell me if that was skipping too many. Derivative of a log is 1 over the argument. So 1 over, and the argument down here is x plus 1 over x. So 1 over x plus 1 over x is the reciprocal of that, which is x over x plus 1. And then and derivative of the denominator here, think of this as x to the minus 1. And derivative of that would be minus x to the minus 2. So that would be minus 1 over x squared. Okay. Now, that's a pretty ugly form. Let's see what happens if we invert the denominator and multiply. Okay. So this would be the limit. I'm only writing the limit so we don't forget the limits there. I'm not writing down what it's going. It's going as x going to infinity. Remember that. Okay. If you invert this and multiply, that's going to be the limit of minus, you're going to wind up with an x cubed in the numerator and a x plus 1 in the denominator. Okay. Hold the phone right there. What is the limit of that as x is approaching infinity? Okay. Divide numerator and denominator by x cubed, and this will give you a 1. This is going to give you 1 over x squared. This will give you 1 over x cubed. Well, 1 over x squared is going to 0, and 1 over x cubed is going to 0. So you would have a 1 over 0, which is, that's not really fair, is it? Something is screwed up here. Mostly me. I hate to do this to you, but we are running close to the end, and it's going to take me some time to clean up a little bit of this mess. Let's go back to this because I think it's all shown here. I think you'll see everything I was doing, but it's going to pick up. So let's go with this, okay? All the techniques are here. We've rewritten this as y is equal to that, which is what we did, and then took a log of that. Log of y is equal to log of this thing. And because that was a continuous function and all that kind of stuff, we can flip the limit and the log. Okay? Now they skipped a step here too. They did the same thing I did. They did x times, they did x times the limit. I did x times the log here, but it comes up, no, I'm sorry. Sorry, I hit the wrong button. They flipped the limit, the log and the limit, and then they also noted that the log of something to a power is x times the log of x times the something. Okay. So that's what they did. They skipped a step there. So log y is equal to the limit as x goes to infinity of x times the log of this thing here. Now I think maybe what they did is now write that. No, this is where I deviated from them, and this is where they were more clever than I. Okay? They rewrote it in this form, which is the log of 1 plus 1 over x, which is exactly what you have here. But now its denominator, right, the x, and basically I did that. You know, I'm sorry, I did do that part, okay? Now, what do we have with this? As x is approaching infinity, this is going to 0. And this is going to 0. Well, 1 plus 0 is 1. Log of 1 is 0. So you're back to a L'Hopital's form. Okay? Now, when you take the derivative of this one, this is where they skipped a couple of dozen steps, okay? Okay. That's what was throwing me. I was trying to follow their, okay. If you were to take the derivative of this, it'd be 1 over this thing, okay? Well, this thing would be, and this is what I was saying before, x plus 1 over x. And I'm sorry, this is where I messed up. I was just taking that divided by x. I forgot to take it over its derivative. And its derivative would be this thing, minus 1 over x squared. I think we got there, or I said it. But I hate it when they skip steps like this. This would be, where's my cursor? Come back, yeah. This would be x plus 1 over x, okay? That's what this turns out to be. The log of that would be x over x plus 1. But then you have to take the log of that. I mean, the derivative of that because of the chain rule. And this shows your 1 over that, which I'm talking about. And then the second part, the derivative of this would be then this again. Well, this now and this can cancel out, okay? And now you're just left with the limit as x goes to infinity of 1 over 1 plus 1 over x. Whereas x goes to infinity, this is going to 0, and this will be 1 over 1, which is 1. So that's the limit of 1 over 1 plus x. See, something really obvious here, they show every step. Up here, they skipped a dozen steps. Well, they skipped a pretty major step. Okay, and you take the limit of this, that'd be 1 over 1 plus 0, and that would be 1. And the limit of 1, is 1. Well, remember, this is the log y is equal to 1. How do you undo a log? Exponentiate. So y would be e to the 1 power, which is e. And that's what I was saying. This form here is simply e. That irrational number 2.71 blah 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 blah. It goes on and on and on. Just like pi is an irrational number, e is an irrational number. It's just different from pi. It's 2.7 something another rather than 3.1415 blah 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 blah. So that's your number e. And that was your example 5. And again, back there was a step. They skipped an awful lot of steps in. All right, let's move on. I think we have time, or do we? Yeah. Now, because you have shown that log of y is 1, you can conclude that y is equal to e, and obtain that the limit as x approaches infinity of 1 plus 1 over x raised to the x is e. You can use a graphing utility to confirm that result, and sure enough, this is what it looks like, and this would be approaching but not exactly equal to 2.71 something another, which is indeed e. The larger x hit, the limiting value there is e. Now, top of page 350. L'Hopital's rule can also be applied to one-sided limits is illustrated in example 6 and 7. And let's see example 6. Do we have time? I think so. Maybe. So let's evaluate the limit as x approaches 0 from the right-hand side only of sine x raised to the x. Well, this looks pretty suspiciously like what we were just doing. About the only way to do this is take a log, because you're raising a base, which is a variable base, to a variable power. So I think we have to go back to, now this is where it might take a long time, because can't do this without the whiteboard, I don't think. So let's clear my drawing so far and go back to it. Now, and by the way, even those without books, you can go to larsoncalculus.com for an interactive version of this type of example. I don't know for certain it'll be exactly like this, but it'll be close enough. I think it will be. I think it'll be exactly like this. The limit as x is going to 0 from the left-hand side. Okay, of, oops, that's terrible, sine x not 6, sine x. Goodness gracious. Not only are the fingers getting tired, the brain's getting tired. Okay. And the eyes are tired, everything is. Sine of x raised to the x. That's the problem. Okay? And very similar to what we did before, we'll set this equal to some value y. Okay? And then we'll take the log of both sides. I'm going to flip sides now. So the log of y is equal to, and all the things applied that applied before, this is a continuous function, all that kind of stuff. So we're going to reverse the limit and the integral. So I'm going to do, rather than the log of the limit, I'm going to do the limit of the log. Okay? That saves me one time of having to write this. Okay? And the x going to, x is going to 0 from the left-hand side here too. And then it'll be the log of, and that log is going to be x times log x. I mean log, goodness gracious, my nose is itching like crazy. X times the sine of x. Okay, I'm skipping steps now too. Sorry about that. Okay, let me make sure I haven't skipped too many. Yeah. I'm sorry, I said it back. I knew there was something wrong with there. It's x times, yuck. Okay. I knew I was skipping too many steps there at once. I'm going to do worse now. Okay. Okay. The log of x sine x is x times the log of sine x. That's what I was meaning to write. So that's the limit of x times the log of sine x. You got two parentheses there, one for sine x and one for that, the limit. And this is now. And I'm pretty sure the next step is going to be to change this to 1 over 1 over x. Because as it sits now, as x is going to 0, that would be 0. And this would be a completely undefined number because log of 0 is not defined. Now, I think what we better do, because of time, we got 1 minute. Yeah. Let's go back to I was afraid this was happening. We may have to just pick up this one next time, or as professors like to say, oh, the rest is left to the student. We've done the heavy lifting here. No. Okay. Here we took the log of both. Here we wrote it as y, took the log of y, both sides, then reversed the order, the limit and the log, just like we had done there. And then this next step here, and they're writing that in, is the limit as x approaches 0 from the right-hand side. I think I was saying the left-hand side, and I was wondering why that. Again, my eyes are bad. That should be from the left-hand side. I mean, right-hand side. I was writing them wrong. I was wondering about that. Okay. And this will be this. Now, at this point, if you were to take that limit, that would be 0 here and the log of 0 undefined. So that would be an infinity there, negative infinity. Okay. So rewrite that as 1 over x, 1 over 1 over x, get it like this, like we had before. Then this is going to, as x is going to infinity from the right-hand side, this is going, because you can't take the log of a negative number. That's why, and the sign of a negative number is negative, so you can't do that. So you have to be approaching this from the right-hand side. And this would be that positive infinity. This is a 0. Log of a positive 0 from the positive side is going to be infinitely large, okay, but negative, okay. This then would be going to infinitely large positive. So you have a negative infinity over a positive infinity, and we're already out of time. We'll have to pick up. I'm sorry. I was going to try to do this, and it just didn't work. We'll pick up in the middle of example 6 next. We'll pick up in example 6. Did we get enough to do homework exercises? Yeah, we almost finished. Homework exercises here would be 3 or 5. They're both at calcchat.com. Any of the odds 7 through 13, they're all at CalcChat. 7's at CalcView. Any of the odds 15 to 41, a lot of those, they're all at CalcChat. 29's at CalcView. Any of the odds 43 to 61, they're all at CalcChat. 51's at CalcView. And I would stop there, okay? In fact, you can stop with 41 if you want to, because these are more like the one we're doing right now. So, yeah, stop at 41, and we'll pick up the rest of those next time. Sorry we ran over, but anyway, any questions? Sorry about that. Any questions?
Yes, I got a question.
Yeah.
When is our first test?
When we finish chapter 5, and chapter 5, we're almost through with 5-6. We're going to do 5-7. It shouldn't be too long. We'll probably skip 5-8. Because we do need to move along. We'll do portions of 5-8. I'll say that. Okay. We'll skip 5-9 for sure. And that's it. So we only have really 5-7, which is next, and a little bit in 5-8. Okay? And then we'll be ready for the test. So it could happen that I could give you the test as early as Wednesday, after class on Wednesday. Otherwise, it'll be next Monday. Okay?
Okay.
All right.
Good.
Any other questions? All right. Sorry, I ran over. Should have stopped before I even started problem 6. All right, I'm going to stop the share. And unless there are questions, I'm going to end the recording, okay? Or end the Zoom. All right. Take care, folks. We'll see you on Wednesday. All right.